So thank you all for attending what will be the final Applied PDE seminar at University of Washington for fall quarter. We are already gearing up for our winter schedule. But today we have, as our final speaker, Jonathan Lotus from SUNY Buffalo. Jonathan is a PhD student at SUNY Buffalo working with Gino Biondini. And he's working on the nonlinear Schrödinger equation, the focusing nonlinear Schrödinger equation with non-standard boundary conditions. And he will tell us about that today. Thank you, Jonathan.
Thanks for the introduction. So as you said, I'm going to talk today about focusing nonlinear Schrödinger equation, non-trivial boundary conditions, and we'll talk about inverse scattering, and afterward talk about some interactions between solitons and dispersive shocks. So we'll start off with a quick background. Focusing nonlinear Schrödinger equation, or NLS, given there, it's a universal model for nonlinear dispersive wave trains. And it describes a range of physical behaviors, such as water waves, plasmas, optics, etc. It's one of the most well-known examples of an integrable nonlinear evolution equation. And as such, the initial value problem can be solved with the inverse scattering transform, which is the nonlinearization of the Fourier transform. Can be roughly outlined as starting with your initial potential q of x0. Through the direct problem, you obtain scattering data at time 0. There's a trivial time evolution, giving the scattering data at any time. And then through the inverse problem, you reconstruct the potential to solve the initial value problem. And so for the focusing NLS, the IST was first developed in 1972 by Zakharov and Shabat. That was for rapidly decaying initial data. And since then, more recently, over the last 15 years, this has been further developed to treat various cases of non-zero boundary conditions. And I'll talk a little bit about some of those in a second. So today in this talk, we're going to talk about counterpropagating wave boundary conditions given there. And this treats the fully general case of plane wave boundary conditions due to the Galilean and phase invariance of NLS. And as I said, there's been numerous works that have been developing this IST for non-zero boundary conditions, and to summarize some of those. First, in 2014, Biondini and Kovacic handled the case of zero velocity, so no counterpropagating waves, just constant boundary conditions with symmetric amplitudes. They handled that using a uniformization variable. This was revisited in 2017 without making use of the uniformization variable. And it was revisited again in 2019 with Bill and Miller, their so-called robust IST. And we'll talk a bit about that later as well. Also in 2014, this was extended to asymmetric constant background, still zero velocity. And then also with a reduction down to a one-sided zero velocity, although in that case, it's not a loss of generality. So those are all IST papers. There's also been numerous long-time asymptotic studies for potentials in this class. In 2007, Buckingham and Venikidis did long-time asymptotics for the Riemann problem. So there's just get rid of the 1 plus order 1 to explicit potential. There for positive velocity. In 2010, Brutato Monvel, Kotlyaev and Shapelsky handled the one-sided Riemann problem. And then very recently, I think in May, the first of these papers appeared. Brutato Monvel, Linnells, and Shapelsky set up the IST for a generic counterpropagating wave boundary conditions, the same here, and then went into the long-time asymptotics, assuming no discrete spectrum. And so that happened independently of our own development of the IST for these conditions. And so I'll try and highlight some of the different things that we go into. Anyway, okay, so the way this talk will go, so sections 2 through 3, we'll talk about the inverse scattering transform, starting with the direct problem, where we'll outline coming up with producing the scattering data. Section 3 will form the inverse problem as a Riemann-Hilbert problem. And then section 4, we'll talk about the solvability of that Riemann-Hilbert problem. And in section 5, we'll look at the behavior of what do solutions in this class do. So we'll look in a certain reduction of some of the outcomes and the dynamics that arise from these potentials. Starting with the direct problem for the IST, and I'll preface this by saying that a lot of this I'll be glossing over some of the details. Some of this is standard, so I'll try to highlight the things that are different from old treatments of the IST. But if you're interested in more details, feel free to let me know. Okay, so the NLS equation is the compatibility condition of the lax pair, which is this overdetermined system of ODEs given here. And the first part we call the scattering problem. So I mentioned that the direct problem, we need to generate this scattering data from our potential. And this is going to include two functions, rho of k, r of k, together with a set of discrete eigenvalues. And then with those discrete eigenvalues, there would be what are called Norman constants. And all of this scattering data we express in terms of the Yost solutions, phi plus and minus. And these are simultaneous solutions of the lax pair that reduce to plane waves for large x. So to get a handle on these Yost solutions, it's helpful first to look at what happens for large x plus and minus. So we know that if the potential satisfies these boundary conditions, these counterpropagating wave boundary conditions, then asymptotically for large x, our solution should look like these exact solutions, q plus and minus. And for those two exact solutions, we can go ahead and we can solve exactly the lax pair for those potentials. And in doing so, in diagonalizing the scattering problem, the asymptotic scattering problem, the eigenvalues are in terms of these branch functions, lambda plus and minus. And we choose the branch cuts on these to be the vertical segments connecting their two branch points. So here the branch cut for lambda plus, if I take positive velocity, is going to be to the left of the imaginary axis, and lambda minus, again, if I take positive velocity v, the branch cut is to the right of the imaginary axis. And again, we take that branch cut to be the segment connecting the branch points. Okay, so so we know that the potential asymptotically looks like these q plus minus, and we have the solutions for, or I should say, we have solutions for those asymptotic potentials. And so our Yost solutions for the generic potential should asymptotically look like those simultaneous solutions. And so that's this portion here are those exact solutions for the asymptotic potentials. It's not really important what all these pieces look like. The couple things I want to emphasize. So there's this factor 1 over d plus minus that we're taking out. We're just rescaling our Yost solutions. And we're rescaling it by the square root of the determinant of E plus minus, which is essentially the eigenvector matrix that showed up in diagonalizing the asymptotic scattering problem. So at the branch points, lambda is 0 at the branch points, of course. And so this matrix becomes singular, and the determinant is 0. And so we're sort of forcing this singularity into our Yost solutions. The bonus is that makes our Yost solutions all have unit determinant, which is helpful. There's some other benefits, but I won't get into that. And this is going to come back later, the fact that we have this singularity going on. Okay, so as a standard, we can make this definition rigorous using Volterra integral equations and looking at a Neumann series. And so the spectrum is going to be the set of all eigenvalues k for which we have bounded solutions. And this is going to include a discrete spectrum, which again we'll talk about as we go forward. And then in addition, we have a continuous spectrum that consists of the entire real line plus the two branch cuts. These are the places where lambda plus and lambda minus are respectively real. And then again, as you go through this Volterra integral equations and study them, it's standard to see that the first column of phi plus and the second column of phi minus are analytic in the upper half plane off of the continuous spectrum, and the reverse in the lower half plane. The second column of phi plus and the first column of phi minus are analytic in the lower half plane. So if you're on the real axis, that's the only place where all four Yost solutions are defined generically. And so you have two fundamental matrix solutions. So they're related by the scattering matrix S of K, which is independent of X and T. If you're off the real axis, as I said, you only have all four eigenfunctions on the real axis. On each branch cut, however, you do have three of the eigenfunctions, one from analyticity, and then one from, you can prove when lambda plus is real, that you have the full phi plus, and the same for minus. So you can extend this scattering relation column-wise, depending on which three eigenfunctions you have. And also the diagonal entries of the scattering matrix, S11 and S22, those are analytic in the lower and upper half planes, respectively, again, away from the continuous spectrum. And so we can take all these analytic pieces and stitch them together to get a new simultaneous solution to the lax pair. So we take in the upper half plane phi plus 1 and phi minus 2. In the lower half plane, we take phi minus 1 and phi plus 2. And then we rescale them by the analytic scattering coefficients that'll help in the Riemann-Hilbert problem formulation. Okay, so this phi now is a simultaneous solution, and it has very nice large K behavior. So if I take the limit as K goes to infinity, this just looks like the simple exponential e to the I theta naught x d k sigma 3. And this theta naught, this is the same phase function that shows up if you were doing IST for zero boundary conditions. So in our Yost solutions, we had phi plus minus that involved the lambdas. In the branch cuts, if you were doing zero boundary conditions, you'd get this theta naught. Okay, so I mentioned the discrete spectrum. The discrete eigenvalues correspond to the poles of phi. And so those are the zeros of S11 and S22. And they come in conjugate pairs. There's a symmetry between S11 and S22. And so if we have a discrete eigenvalue, I'll label it by the one in the upper half plane, Kn, then there is some Norman constant Cn that gives relationships between the residues of phi and the columns of phi. Okay, so as I've already mentioned, this phi is discontinuous on our continuous spectrum. Part of it is discontinuous because of the way we defined it in upper and lower half planes. So we're sort of forcing a discontinuity across R. But there's also discontinuities across the branch cuts because the Yost solutions are discontinuous across the branch cuts. And again, that's because we're normalizing those Yost solutions at plus or minus infinity and diagonalizing those asymptotic scattering problems, the eigenvalues are branched. So let's clarify some of the notation. As we've been using, we'll continue to use subscripts plus and minus to refer to normalizations as x goes to plus and minus infinity. But now we'll throw in superscript plus and minuses are going to designate projections from the left and right side of the continuous spectrum sigma. And so we want to understand the discontinuity of phi across this across the continuous spectrum. So for K and R, we can just use the scattering relation and then rearrange things to come up with this jump condition. If you're on the branch cuts, then you look at some of the symmetries of the scattering problem and then play a similar game of rearranging things. And so we find that the projection from the left of phi is equal to the projection from the right times this jump matrix J given here. I'm clarifying the jump matrix in the upper half plane, and there's a symmetry that gives the corresponding jumps in the lower half plane. And I'll emphasize, so I mentioned earlier that the scattering data for the direct problem is going to involve two functions, rho and r. So these two functions show up in our jump matrix, and they're given in terms of the entries of the scattering matrix. Okay, so more or less that's our direct problem. We started from our potential. We generated our reflection coefficient rho of k. We have this other function r of k that's appearing in the jump matrices. We have the discrete eigenvalues that are coming conjugate pairs. And then for each pair, we have a Norman constant. There's one more piece of information that will be included in our scattering data, but I'm going to hold off on talking about that for now. And so in preparing for the inverse problem, which, as I said before, we'll formulate as a Riemann-Hilbert problem, we're just going to make a small transformation to our solution to the lax pair phi. by removing these large K oscillations. So M, after factoring out that e to the I theta naught, sigma 3, M goes like identity as K goes to infinity. And so we're going to formulate the inverse problem as a Riemann-Hilbert problem, which has this matrix M as a solution. And so to do that, we'll just translate those residue conditions that I stated for phi into residue conditions for M, which is simple enough. We just pick up some exponentials. And same thing with the jump condition, translate that jump relation for phi into a jump relation for M. Again, we just pick up some conjugation by exponentials. Okay, so now we can move on to the inverse problem, which we'll formulate as a Riemann-Hilbert problem. So we saw in the direct problem that we used this potential Q of xt to define this matrix M that satisfied certain properties. And now for the inverse problem, we change perspective. Now the thought process is, if we're given a suitable set of scattering data, can we find a matrix M that has these properties? And then from that matrix M, can we reconstruct a solution of NLS? And so let's define this Riemann-Hilbert problem that has all those properties we found. So to clarify, I'll try to always use a capital M to denote our solution that we generated from the direct problem, and then a lowercase m to denote some matrix that we're looking for this Riemann-Hilbert problem. So we want to find a matrix M satisfying these conditions. It has the right analyticity, analytic everywhere except the continuous and discrete spectrum. It satisfies the jump relation, and it has simple poles that satisfy the residue conditions that we saw before. And then it has this normalization. It goes like the identity as K goes to infinity. And so the important detail that makes the IST work is that this Riemann-Hilbert problem is formulated only using knowledge of the initial potential. So all of the scattering data that we generated, you can get at time 0. And so that gives us this trivial time evolution is basically baked into the Riemann-Hilbert problem. The other thing I'll note is that this Riemann-Hilbert problem is not quite complete, and we'll need to supplement it with one more thing. I mentioned before that we've got one more piece of scattering data, and so that those are tied together. So the first theorem, we have this Riemann-Hilbert problem. Supposing we can find a solution to the Riemann-Hilbert problem, the reconstruction is simple. If we have a solution, then it's just minus 2i times the limit k goes infinity of k times the 1, 2 component of our solution M. And then the other piece of the puzzle is that if we have a solution M of the Riemann-Hilbert problem, here I'm just omitting the x and t dependence for brevity, then it's a solution of this linear algebraic integral system. And so in this way, we've linearized the initial value problem. Okay, but there's a problem with this formulation of the Riemann-Hilbert problem is that we're not guaranteed a unique solution. And as an example, we can consider two different potentials. One I'll call Q background, which is just a constant background with a phase, the time phase, so e to the 2it. And then we also have the Peregrine solution, which has the same constant background, but now it has a localized in space and time peak. And both of these solutions generate this same scattering data. They're both reflectionless. There are no discrete eigenvalues. In this case, the function r doesn't show up because we're taking 0 velocity at equal amplitudes. But that's not so important. But what's important is they generate the same scattering data. And on the other hand, each one generates their own matrix, M background and MP. But they satisfy the same Riemann-Hilbert problem, right? The Riemann-Hilbert problem is stated in terms of the scattering data. It's the same scattering data. It's the same Riemann-Hilbert problem. So clearly, there's not going to be a unique solution to this Riemann-Hilbert problem. So what is the difference? What is the distinguishing feature between these two solutions? And it turns out that the way they differ is with their behavior toward the branch points. So as I mentioned, for these two potentials, the continuous spectrum is just the crosses, the real axis plus the segment from negative I to I. And at the branch points I and negative I, the background solution blows up with a 1/4 power singularity, and the Peregrine solution blows up with the 3/4 power singularity. And so that's where we see the difference between these two solutions. Oftentimes, Zhao's vanishing lemma is used to give a framework for proving the solvability of Riemann-Hilbert problems like these. But in this one that we formulated here, it doesn't apply because of this singular behavior at the branch points. So the question becomes, can we supplement our Riemann-Hilbert problem with conditions that will give us uniqueness of solutions? And so to kind of motivate how we'll do this, we'll look back at the direct problem. So our EO solutions, T plus minus, as I mentioned before, because of that factor D plus minus that we're factoring out, they have this 1/4 root singularity at the branch points. And the scattering coefficients, we can express them as Wronskians of the EO solutions. And so they also are going to inherit these 4th root singularities at the branch points. They could potentially have higher or I guess lower, you could cancel out the growth in the scattering coefficients potentially by some linear dependence between the EO solutions. So in essence, the matrix M, the growth of M at the branch points is determined by what happens to the scattering coefficients. And I'll just clarify now that S22 and S11, they have this short symmetry. And so really, we just need to worry about one of them and the other one follows from that. So for the simplest case, we say we're in the generic case if S22 has 1/4 power growth at the branch points, which corresponds to the case where these EO solutions, phi minus 1 and phi plus 2, do not become linearly independent at the branch points. And so in that case, in the generic case, the growth of M is characterized, we describe it by the fact that these following limits exist. If I approach the minus branch point, M is continuous. If I approach the plus branch point, then the growth of M can be canceled out by this K minus P plus to the sigma 3/2 and the other in the lower half plane. And I'll just clarify real quick, back to the distinction between our background solution and the Peregrine solution, that's exactly what's going on here. In the background solution, the scattering coefficient does have the generic case 1/4 power blow up at the branch point, whereas in the Peregrine solution, there's a virtual level at that branch point, and there's some linear dependence between the eigenfunctions, and that's what gives this different growth. Okay, so we're going to take this extra behavior that we see about M from our direct problem and throw that into our Riemann-Hilbert problem as growth conditions, and we'll see that adding the requirement that these limits converge to our Riemann-Hilbert problem is what's going to give us a unique solution. And so to make this argument, the first thing we'll do is formulate a modified Riemann-Hilbert problem. This is based on Billman and Miller, the robust IST that I mentioned before, that sidesteps all these difficulties with branch cuts and branch points and poles. And for that modified Riemann-Hilbert problem, we're able to prove uniqueness. And then we'll construct a map between the two Riemann-Hilbert problems that we can use to walk back to our original problem and prove uniqueness there. Okay, I guess I'll pause for a moment and see if there's any questions before jumping in. But as I said, the next phase we'll be talking about this uniqueness of solutions.
Actually, I'll ask a question.
Sure.
In the periodic case, the spectrum that's off the real axis is not actually straight line vertical segments; they're actually curved segments.
And gaps, yeah.
Well, but they're curved. So for the whole line case, they're actually straight line segments, just vertical segments.
At least for these plane wave boundary conditions, yes. They're going to always look like the real axis plus one vertical segment each for the left wave and the right wave. And then depending on if you take like zero velocity, then those branches come together. If you take symmetric amplitudes, then you get just a single piece on the imaginary axis.
Right, in which case the symmetry is going to force it to be
yeah.
But even when they're off the axis, they're still just vertical segments.
Again, I'll say I don't know of any examples where that's not true, but I can say at least for these counterpropagating wave boundary conditions, then that is the symmetry, or that is the spectrum. I should say it's, let's see.
Probably the hello, this
yes.
Alexander Tovbis. Probably you can move a little bit this vertical contour without changing solution of Riemann-Hilbert problem.
Yes. It's not a question about the choice of branch cuts, but the statement was that this was this was actually where the spectrum was.
Yeah, it's very simple. It comes because this is the set of values of k for which lambda is real.
Right.
By the way, there's a typo in E plus minus. The denominator shouldn't have x and t, right?
Correct.
So it's a small typo.
That should be a v over 2, I think.
Okay, so but it's a straightforward calculation to calculate the continuous spectrum, and you find out that it is just the vertical segments.
Yes.
Correct.
Yeah, as I said, it's just when lambda is going to be real.
Okay, thank you.
Bernard, can I say one quick thing about that? Gino's explanation is exactly right, but one other interesting thing is if you cut off the potential, so you make it compactly supported, you'll see, and then make the support go to infinity, you'll see the eigenvalues accumulating on these two bands.
Okay, thank you.
Okay. So just to recap, we want to prove uniqueness now of this new Riemann-Hilbert problem with these added growth conditions for the generic case. So I mentioned before when I introduced the O solutions that they're discontinuous across the branch cuts, and that was again because of this normalization. We're normalizing them to be plane waves at plus or minus infinity, and those asymptotic scattering problems are branched. But you could choose any other point at which to normalize your solution to the lax pair. And so again, this is Billman and Miller recently did this. And so we'll introduce a new solution that's normalized, which is pig 0, 0 for convenience, but any point will do. So let's let psi be the unique solution that is normalized at 0, 0 to be identity for all k. And the key property here is that this psi is an entire function of k. So there's no, we don't have to worry about branch cuts, branch points, anything. We can also relate psi to our earlier phi function, which we defined in terms of our U solutions. Quite simply, psi is just going to be phi times this matrix I'm calling C naught, which is just, or times C naught inverse, where C naught is just my phi function evaluated at 0 and 0. In fact, it'll work for any simultaneous solution to the lax pair, but we'll stick to the one we've already generated. And then I'll just emphasize that this C naught is, again, computed just from the initial potential. And so we're not going to ruin solving the initial value problem. We're only using the initial potential to evaluate this C naught. And so the idea is to replace phi with psi when we're near the branch cut and poles, because psi is analytic there. And so we'll just let BR be the ball of radius R, and we'll fix an R big enough so that this ball contains both branch cuts and then all discrete eigenvalues that were specified in our Riemann-Hilbert problem. And then we'll have this new jump contour sigma tilde, which is just the real axis outside the ball plus the boundary of the ball. And so we'll introduce a new M, I'll just call it M tilde, where, as I said, we'll use phi outside the ball and we use psi inside the ball. Again, we'll factor out these large K oscillations that we saw in phi so that M tilde goes like identity as K goes to infinity. And we can equivalently represent M tilde in terms of our old M. Outside the ball, it's the same M, and then inside the ball, it's just the old M with this conjugated factor on the right of C naught. And so one question is what Riemann-Hilbert problem does this M tilde solve? So introduce a new Riemann-Hilbert problem, the modified Riemann-Hilbert problem. Now we seek a matrix M tilde that satisfies these conditions. We want M tilde to be analytic in the complex plane away from our jump contour. It satisfies this jump condition on the contour where our jump matrix is given by this J tilde. It's fairly straightforward to see where this comes from. If I'm on the real axis outside the ball, then M tilde is the same as M, and so it satisfies the same jump condition. If I'm on the boundary of the ball, the definition here of this M tilde makes it pretty clear. It's just quick algebra to see what the jump condition should be, and it's either C naught or C naught inverse. And then again, for the same reason, since M tilde matches M outside the ball, it has the same normalization at infinity. It goes like identity. And so I'll emphasize that this Riemann-Hilbert problem, there's no mention of poles or growth or at the branch points or anything to do with that. And essentially all that information about the discrete eigenvalues and the growth behavior at the branch points is captured by this C naught matrix. If you were to analytically extend C naught, I'll say first, from the point of view of the Riemann-Hilbert problem, C naught is only defined on the boundary of the ball. But if you were to analytically extend that C naught, then you would recover the location of the discrete eigenvalues and the residue conditions and the growth behavior at the branch point. But the advantage of this modified Riemann-Hilbert problem is that because all these issues are removed, there's no poles, no growth or anything, we can use Gauss vanishing lever to establish the existence and uniqueness of solutions for this modified Riemann-Hilbert problem. And so the reason we went through all this was we're trying to get uniqueness of the original Riemann-Hilbert problem. And so that's one question is, how do we use uniqueness of this modified problem to establish uniqueness for the original? And so to do that, we're going to define a map F naught. For now, I'll just think about this as operating on any matrix valued function. And so if I stick in M, then motivated by that kind of construction we did from the direct problem, we'll just define F naught M to be M if I'm outside the ball. And I have to also exclude the real axis because, well, I guess at this point I don't, but in a second I will. And then if I'm inside the ball, we'll follow that same kind of mapping that we had. We'll just have M multiplied by this conjugation of our C naught matrix. Okay. And so, as I said, we're going to use this map to prove uniqueness. So the question is, what does this map do to solutions of the original Riemann-Hilbert problem? And so let's suppose M is any solution to the Riemann-Hilbert problem. And I want to just clarify that so we picked this C naught matrix from a particular solution to the Riemann-Hilbert problem that we generated from the direct problem. But now I'm taking any old M that might be a solution to the Riemann-Hilbert problem. And so it's clear that from the way we define this map that if I take F naught of M, then it's going to immediately satisfy the normalization, again, because it just matches M outside the ball. It's also easy to check that it satisfies the jump conditions. Sorry, I'll get there in a second. It's immediately clear that outside the ball, it satisfies the jump conditions and it's analytic because, again, as long as I'm outside the ball, then F naught of M is exactly the same as M, and the Riemann-Hilbert problem for M specifies all those conditions. So the only question is I guess two questions: what happens on the boundary of the ball, and what happens inside the ball? So as I said, that's the question: is F naught of M going to be analytic in BR? First of all, we can show pretty easily that so. I'll say in principle, we're taking M to be a solution of the original Riemann-Hilbert problem, which means M has jumps along sigma inside the ball. So that's the real line and then these branch cuts. However, C naught was also a solution to that Riemann-Hilbert problem. And so it also has jumps along the real axis and the branch cuts inside the ball. And so it's easy enough to check that the discontinuities of any solution of the Riemann-Hilbert problem and the discontinuities of this C naught that we've designated, those cancel one another out. And so we have identity jump inside the ball. So we're analytic on this continuous spectrum portion. you can play the same game with the residue conditions. M has, it solves that Riemann-Hilbert problem. It has some residues. C0 solves that Riemann-Hilbert problem. It has residues, and they cancel each other out. And so at all the discrete eigenvalues, F naught M has 0 residue. So it's analytic at those points as well. And then the only question left is, what about the branch points? Is F naught of M going to be analytic at the branch points? So it turns out for the original Riemann-Hilbert problem without growth conditions that we stated first, that's not enough to guarantee that F naught of M is analytic at the branch points. However, if we throw on these generic growth conditions, if we require that M satisfies these same growth conditions, then essentially the growth of each cancels each other out in F naught of M. And so we have well-defined limits at all the branch points. So it is analytic there. And so we have this lemma essentially just says, saying that this map takes solutions of the original Riemann-Hilbert problem that satisfy the generic growth conditions, and it sends them to solutions of the modified Riemann-Hilbert problem. But we already know the modified Riemann-Hilbert problem has a unique solution, and so we can use the invertibility of F to pull that back to the original Riemann-Hilbert problem and see that it must have unique solution satisfying the generic growth conditions. And I'll add a note that so this is all talking about the generic case where the analytic scattering coefficient, or where the Yost solutions remain linearly independent as you approach the branch point. But you can make similar arguments. If they become linearly independent, you can describe the rate at which they become linearly independent and then make adjustments to this map to capture the same kind of result. Okay, so up till now, we've been talking about the inverse scattering transform. And so we've got this formulation. And the inverse scattering transform lays the groundwork for doing long-time asymptotic studies of solutions. And so now we'll talk about what do solutions look like in this class of potentials? What kinds of behavior can we see? So we'll talk about, we're going to talk today, or right now, I'm going to talk about one-sided boundary conditions. So here I'm going to take A minus to be 0 and A plus to be, I'll just drop the plus and call it A. And for one-sided cases, you can, without loss of generality, take 0 velocity and 0 phase difference. So we'll do that. So let's consider first just the pure Riemann problem, 0 less than Q step, I'll let 0 for x less than 0 and A for x greater than or equal to 0. And so when you carry out the long-time asymptotics, what you find is dispersive shock waves. And these are confined to this region x between 0 and 4 root 2 AT, which I've designated by these dashed lines showing the boundary of the DSW. So those edge velocities are 0 and 4 root 2A. So we can also look at just taking 2 pure soliton solutions, one type on a 0 background, one type on a non-zero background. And again, we'll take the amplitude to be A. And so when you're going through that same formulation in the IST, when you're generating the Yost solutions, those Yost solutions contain these exponential phase functions, depending on the background. In the 0 velocity case, we just have the phase function as k x minus 2 kt. That's the same theta naught that we used, not for our Yost solutions previously, but when we were setting up the Riemann-Hilbert problem. In the non-zero case, we've got lambda x minus 2 kt, where lambda is just k squared plus a squared square root. That's the same lambda as before, just with 0 velocity. We had lambda plus and minus before. And so just to kind of see the difference, qualitative behavior between these 2 types of solitons. Here's just the initial profile of a 0 background soliton. It's a sesh traveling. And here's the profile of a non-zero background soliton. It's a breather traveling. And so we want to see what happens when we now put these 2 things together. We have these dispersive shock waves coming from an initial step. We have these solitons. And so how do they interact? And so we'll take a superposition of this Q step and either a zero background or a non-zero background soliton, and we'll send that soliton toward the DSW and see what happens. So here's just two examples of that. And we see what looks like, here's this initial zero background soliton traveling through the DSW and emerging on the other side now as a breathing soliton on the non-zero background. And then the reverse in the other case, I send a zero background soliton through the DSW and it emerges now as a soliton on a zero background. But the spectrum doesn't change, right? So the solitons correspond to discrete eigenvalues. That doesn't change with time. And so the question is, how do the velocities change due to this interaction? So as I mentioned, the solitons arise from the discrete eigenvalues in the IST. And if we have a pure soliton generated by a discrete eigenvalue k naught, then its velocity comes from the exponential phase function that we saw in the O solutions. So if we're studying the long-time asymptotics, typically we're looking along a ray c equal x over t. And we'll define these controlling phase functions, capital theta zero background and capital theta non-zero background, where we just take the phase functions we saw in the O solutions and we factor out t. So k, c minus 2k for the zero background case, and lambda c minus 2k for the non-zero background case. And so as you go through long-time asymptotics, you find a localized contribution with velocity c exactly when the imaginary part of this controlling phase function is 0. And so it's easy enough to solve these two things. For the zero background case, you've got the velocity is just going to be 4 times the real part of the eigenvalue. And for the non-zero background case, it's twice times the real part plus the imaginary part times real part of lambda divided by imaginary part of lambda. Okay, so let's return now to some of these cases. If I look at a non-zero background soliton, so starting on the right side of the step, sending it toward the DSW, and looking at this interaction. So here the red dashed line gives the velocity of this initial non-zero background soliton, and then the blue dashed line gives the corresponding velocity of a zero background soliton that would be generated by the same discrete eigenvalue. And so we can see that there's this change of velocity in each case, and the initial non-zero background soliton is transmitted through the DSW, emerges on the other side as the corresponding zero background soliton with the same discrete eigenvalue. And so as such, it's on its new background, it has a new controlling phase function, and so its velocity is governed by that controlling phase function. So what about the other case? If we start with a zero background soliton and send it toward the DSW, here things are more complicated. So in this left plot here, it looks similar behavior. I start with this initial blue velocity for the zero background soliton, and then once it enters and actually passes through the DSW, maybe it's not totally clear, but it emerges with the red velocity given by the corresponding non-zero background soliton generated by the same discrete eigenvalue. However, in these other three panes, these are just other selections of eigenvalues. We don't see anything traveling with this non-zero background velocity. We do see something trapped in the DSW, and so we want to understand what is this structure in here, and what is, at least for now, what is the velocity of this structure in there. So to get a handle on that, we need to introduce 4 different regions: D1, D2, D3, D4, and these are based on the level curves of this velocity function for a non-zero background soliton. And each of those 4 plots we saw before corresponds to one of the 4 regions. And so these 4 regions will separate the possible outcomes of the interactions. D1 and D4, these make up the places where the non-zero background velocity is greater than the DSW edge velocity. So you remember that the DSW edge velocity was 4√2a. And so D4 and D1 are the set of eigenvalues where that non-zero background soliton is faster than the DSW. D2 and D3 are the regions where that non-zero background soliton is slower than the DSW. And I'll come back and clarify the difference between D2 and D3 in a moment. But we have these 4 regions, and to get a handle on the velocity of these trapped structures, we're going to make a comparison first with Biondini, and Mantzavinos in 2018 did a long-time asymptotics, not for a step with soliton, but for a pure two-sided non-zero background with the soliton and a localized disturbance. In that case, the localized disturbance also generates a DSW. Instead of the half wedge we saw for the step problem, we have a two-sided wedge now confined to the region negative 4 root 2 AT to 4 root 2 AT. And so again, as you go through the long-time asymptotics, we're looking for, we saw that for the solitons, we got contributions to the solution when the imaginary part of our controlling phase function was 0. However, inside the DSW, the controlling phase function has to be modified. And so it's instead of having this theta non-zero background, it's replaced with this abelian integral h. It's not too important, the details of what this h looks like. I'll just say it includes this parameter alpha, which is determined by a system of modulation equations governing the DSW. And so again, in this case of this constant background with localized perturbation, when you introduce a soliton, you find localized contribution to the solution with velocity xc when the imaginary part of this modified controlling phase function is 0. And so now we can clarify these regions, D1, D2, D3, D4. They are what separate the possibilities for the roots of the imaginary part of h of ck. And so in D1, there's no roots. In D2, you have a single crossing root, which we'll draw in yellow. In D3, you have one crossing root and one non-crossing root, which we'll draw in green. And then in D4, you have a single non-crossing root. And just to clarify, the separation between D2 and D3 is traced by the trajectory of alpha as c goes from 0 to the velocity of the wedge. And so we can now denote Vs, k, is going to be the value of this crossing root if I'm in D2 or D3. And V star is going to be the value of the non-crossing root if I'm in D3 and D4. And the key is that so again, that was all for pure non-zero background, localized perturbation in soliton, but we can use that same modified controlling phase function to predict the velocity of soliton trapped in the one-sided DSW. And so we see for K in D1, the soliton is transmitted. That was one of the plots earlier I'm omitting for now, since nothing's changed. For K in D2, the soliton becomes trapped with this velocity V sub s. And if I'm in D3 and D4, the soliton leaves we call a wake with velocity V star of K naught. It's easier to see, I mean, you can kind of see these structures in here. It's much easier to see what's going on if you subtract out the pure DSW from the density plot. So that's these plots here. I've just removed that DSW, and now you can clearly see this structure inside the DSW traveling with velocity Vs for D2. Traveling with V star for K and D3 and something traveling with V star for K and D4. Unfortunately, because of we're working in double precision and because of the modulational instability of focusing on LS, we're very limited in how long we can simulate these, and so we're not able to see, for example, in D3 the trapped soliton traveling with velocity Vs, and we're not able to see in D4 the emergence of a non-zero background soliton on the other side. Okay, and so just to make some closing remarks, again, these observations above, those are based on this long-time asymptotic study for constant non-zero background with soliton localized perturbation. But we didn't do any full nonlinear long-time asymptotics using the Dive-Zhao nonlinear steepest descent, which would be necessary to prove these observations, to prove that these trap structures have these velocities. On the other hand, the inverse scattering that we presented earlier gives exactly the foundation for doing these long-time asymptotic studies. And so I'll just mention some of the cases that have already been looked at. So I've mentioned again for the symmetric constant background amplitude, 0 velocity, so no counterpropagating waves with soliton localized perturbation. That was in 2018, Biondini, and Mantzavinos. The plots we were just looking at, the arguments we were just looking at, was in 2019 by myself and Biondini. That was for a one-sided step, again, with no velocity, although that's not a loss of generality. And then very recently, Tiedemann, Nels, and Shapelsky looked at the long-time asymptotics for the fully general counterpropagating wave boundary conditions, but in the absence of a soliton. And so the question still out there is what happens in this for generic plane wave boundary conditions? What happens to the soliton in these different DSWs? And there's just a sampling here of pure Riemann problems for these generic boundary conditions. Unequal amplitudes. Here's a zero velocity, a negative velocity, and a positive velocity. And you can see certainly in this case, I mean, in the other two, I could make pretty good guesses as to what happens to the soliton depending on its velocity. But in this third case, where now these waves are coming together, we have higher phase oscillations and higher genus regions, and then things become much more complicated. And that's my talk, and there's some references.
Lots of virtual applause as well.